warahmatullahi wabarakatuh. Hello everyone, let me introduce myself. My name is Novia Mita Safitri. I'm from Group 4. I think fluids are fascinating and awesome. Understanding of fluid is incredibly useful because anything that flows, liquid or gas, is fluid. So, water counts, but so does air and so does consider. Using their knowledge of fluids, physicists and engineers can design things like pressure sensor, hydraulic pumps, and airplanes. But first, let's start with the physics of fluids at rest. Until now, we've often described the physics of objects based on their mass. But when it comes to fluids, we must use a different quality. Density represents an equation by the Greek letter rho. You're probably familiar with density. It's mass divided by volume and measured in kilograms per meter squared. And there's another important quality of fluids one that scuba divers and mountain climbers think about a lot: pressure. In our last episode, we defined pressure and apply force divided by area, measured in units of newtons per meter square. Now, as Pascal and fluids apply pressure in every direction. So right now, there's air putting pressure on you and me from every side. In fact, the average air pressure at sea level is 101,325,000 pascals, and if you jump in pool, the water would also exert pressure on you. But if you've ever tried diving to the bottom of a pool, you'll know that there's more pressure at the bottom than at the surface, which is why at the bottom your ears hurt and your head feels like it's about to implode. That's because the deeper you go, the more fluid there is above you, with its weight pressing down. There's an easy way to calculate the pressure of fluid at a given depth. It's just the fluid's density times small g times the distance to the surface, represented by the letter H for H, and the change in pressure based on depth is equal to the fluid's density times small g times the change in distance to the surface. The density of water is 1,000 kilograms per meter squared, and the change in distance to the surface is 2.775 meters, which means that the pressure at the bottom of the pool is 27,000 pascals more than the pressure a quarter of a meter down. So, let's say you're swimming in a pool that's 3 meters deep and you want to know how much more pressure you'll experience at the bottom of the pool versus how deep you are now, which is, let's assume, a quarter of a meter. So, if you want to apply a lot of force to lift something heavy, for example hydraulic are the way to go. Now, if you're going using pressure to the stove, you're probably to want to be able to measure that pressure, which is where manometers and barometers come in. A manometer is just a U-shaped tube with a fluid inside. Say you want to use one to measure the pressure of a bike tire. You'd stick one side of the tube in the tire and leaving the other side open to the atmosphere. If there's a difference in the pressure on each side of the manometer, whichever side has the higher pressure will pass the fluid away from it, creating a difference in the height of the fluid on either side of the U. In this case, the inside of the bike tire has a much higher pressure than the atmosphere, so the level of the side of the U that's closer to the tire will be lower. If you measure the difference in fluid height directly, you'd get what's known as gauge pressure. The difference between atmospheric pressure and the pressure inside the tire, but the actual pressure of the tire in absolute pressure is the atmosphere pressure plus the gauge pressure, so the pressure inside the tire will be equal to the atmospheric pressure plus the density of the fluid inside the manometer times small g times the difference in the height of the fluid. Barometers, on the other hand, use a long, vertical tube that's closed on one end, usually filled with mercury and then stuck upside down in a bowl that's also full of mercury with the closed end of the tube at the top. The pressure of the atmosphere passes down on the mercury in the bowl, which keeps a certain amount of mercury in the tube. At standard atmospheric pressure, the mercury in the tube will be easily 76 cm high. If the air pressure goes up, so does the level of the mercury, and vice versa.